Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is our 5th anniversary. I'm so pleased you could all come join us. I hope you're going out to the demo floor and seeing some new and interesting research. I'll be introducing Byron shortly, but I just wanted to let you know we have these lectures packed pretty closely back to back, so we ask that you hold your questions until the end. Byron will talk for about 40 minutes. It'll give you guys about 5 minutes for Q&A, and then Byron will go out to the speaker's corner at the Berlin Wall if you have any further questions. As you can see, Byron's talk today is on the applications of automated reasoning. He's looking at doing automated reasoning in new and interesting concepts and not just chasing and hunting down bugs anymore. He did his undergrad at Evergreen and did his PhD at the Oregon Graduate Institute, is currently flying all over Europe for way too cheap, and is clearly a very nice man because he's been laughing at my stupid jokes for like half an hour now. So please help me welcome Byron Cook.
Thank you. So all of you have pointers, you can help along, but I have 2 pointers, so I can zap back at you if you point at me. So I used to be a developer in the Windows division. I worked on a tool called Static Driver Verifier in the kernel team, and now I'm at Cambridge. So I'm going to tell you about something that I've been working on and using both as a developer and also as a researcher. So I don't have a particular tool to push on you, but I instead want to tell you about a trend that's going on in computing, and this might affect the way that you develop code in the future or tools that you might use in the future. And I will also tell you about some tools that are in development in Microsoft Research, but they're not really tools that are products with product support and that sort of thing. So I'm going to tell you about proof engines. So these are automatic software libraries that answer questions posed in logic. Okay? So in the past, these proof engines were toys. They were sort of toys for PhD students looking for dissertation topics, or researchers trying to get tenure, or hobbyists and that sort of thing. Okay, and they weren't really powerful enough for real developers to use, right? To use on real problems that you hit when trying to solve problems for real customers. Okay, and after 50, 60 years of trying to solve this proof engine problem for logic, it turns out that now actually they're starting to scale to real problems. So it's time actually to revisit this question about proof engines and whether or not they can be used in industrial code. Okay, so I'm going to tell you about what proof engines are. I'll give you some inkling as to how much they can scale, and I'll give you some ideas on how they might be used. Okay, so we'll start with an introduction to proof engines. So here's an example of a question that we might ask in a proof engine. Okay, now this is the one non-alphanumeric symbol I'm going to use in the talk. Okay, so this question says, for all x, so x is a variable and it could range over, let's say, all integers. So for all x, y, and z, if x is less than y and y is less than z, then is x less than z. Okay, and you should think about that for a moment and convince yourself that that's true. So this is albeit quite small, but the flavor of the sort of question we might ask a proof engine. Okay, and in code, this is sort of a similar question. So if we know nothing about x, y, and z when we hit this code, is it possible to call error? Right, same question. So the idea of a proof engine is that it's supposed to be sound, right? It's a catastrophic error if a proof engine says that something is valid and it's not valid, right? So the idea is that a proof engine is sound and it will only return valid if the thing is provably valid. Some proof engines are complete, which means that they will not say something is invalid unless there's actually a counterexample to the claim, okay? So one thing we have to be careful about when looking at proof engines is we need to be clear about the APIs to the proof engine. What is it that the proof engine supports, and what doesn't it support? And the proof engines differ on this, right? There are many different proof engines, and they support different logics. So we have a whole bunch of Lego blocks that we could use to build up a logic, and some proof engines support some subsets of this. So for example, most proof engines will support this. So most proof engines have and or, not, true, and false, right? We might have variables that range over Booleans. So our variables might only be able to take on the value true or false, or they might be over the arbitrary length integers, so all real true integers. Or they might be over 64-bit integers. Okay, so this is something we have to keep in mind. And when we talk about proof engines, we need to be clear on the logic that they support. And we might have this for all. We might have plus or minus. We might have equality. And we might have things from programming languages like pointers and so on. So all of this that I've told you thus far was known in 1962, right? In 1952. But the reason that I'm bringing up this old dead history is that now these tools that solve these puzzles are really amazing now. They're really, really high performance and can handle quite large problems. So it's now practical, possibly, for us to begin using them in commercial applications. Okay. So I'll now tell you about this. So here's. This sort of gives you a flavor for this sort of scale that we see nowadays. So this comes from a talk by a professor from Princeton, and it's for this logic. So we're talking about false, true, and or, and variables over Booleans. So on today's hardware, so if we were to take tools from 1952 on today's hardware, there were tools that could reliably handle puzzles presented to it in this logic with perhaps 20 variables. Right? So you could have 20 propositional variables, and you could reliably solve that. Right? Tools from 1952 on today's hardware. Okay? And we saw pretty much the same thing up until 1982. So maybe the proof engines could explore 2 to the 40 possible configurations, right? So for each variable, we have to consider whether or not it's true or false when we're trying to prove that for all possible values for each variable, the thing is true, right? But starting in the early 90s and then in 2002, we saw really tremendous growth in the number of variables that could be handled. And so now we can pretty reliably handle 2 to the 10,000. Okay. So, and this has been achieved by harnessing the Darwinian competitive spirit of people. So there have been groups all around the world, university groups and industry groups that have been working on this particular problem and competing with each other. Okay. So for every year, there's a competition. And we can just look at the results of this competition. So these are the software libraries that solve this problem for propositional logic. That's variables over true and false, and or not, and then also true and false. And we can look at how they do. So how this is the time taken for each benchmark. And how you read this is, so let's take one of the not so good solvers. So here, this solver for, let's say, the first 25 problems was able to solve them in effectively no time. But then it started on the 26th puzzle, it needed around 200 seconds. Okay, and then it was able to solve a few at 200 seconds, and then after that, it timed out. So there were about 100 examples that it couldn't solve, okay, from this competition. And these are examples that are actually provided by industry. So there's the handmade category, and there's the random category, and then there's the category of puzzles given to the competition by companies. Okay, so that's not so impressive, but this one is really impressive. So this is called Forklift, and it solved all 143 benchmarks provided by industry. So there was not one benchmark from industry that it wasn't able to solve. And it solved them all. Each of the hardest one was about 850 seconds. So let's look at a few examples of these proof engines. So this is one of the competitors in that competition I told you about. This is called ZChaF, and it's from Princeton University. And it was written by a number of people. One of them, Lintao Zhang, is now at Microsoft Research, and that's wrong. Should say Silicon Valley. And this is a complete proof engine, so it's sound and complete. So it will say something is not true only if there really exists a counterexample to its claim. And it also provides the counterexample. So if you run the tool, it will give you the counterexample. Okay, so here's 3 examples it was run on. So the Gigamax cache coherency protocol, there was a tool running verification of Gigamax cache coherency. There were, in this example, there were 10,000 propositional variables, so 10,000 variables that could take on true or false. And it was proved valid in 5 seconds. Okay, so that's 2 to the 10,000 possible configurations that it explored in 5 seconds. And it said for all possible configurations, all those 2 to the 10,000 possible configurations, this expression will always result in true. Yep.
It couldn't solve all 10,000 variable problems.
It did. It did. There will not be a setting to the variable such that it will be false.
No, what I'm saying is that it can't solve all 10,000 variable problems. This particular problem it can do quickly, but there are others.
Yeah, that's right. And here's another example: 63,000 variables this is generated by a tool that's verifying a FIFO queue from a company called Galileo, which makes telecommunications hardware. And this found a counterexample to this claim in 8 seconds. Okay, so that searched through 2 to the 63,000 possible configurations and found one where it failed. Okay, oops. So here's another example. This is for a richer logic. This is called Euclid. And I think one of the authors is back in the back room somewhere. That's Shivendu Lahiri, who has also joined us at Microsoft Research in Redmond. And this has been used a lot for verifying models of out-of-order superscalar microprocessor models. So here's a couple of examples where it's been run. So notice it supports less than or equal, plus and minus, variables over true integers. One example had 104 integer variables. So that's infinity to the 104, which is a pretty large number. Possible configurations to all the variables. It had 2,500 Boolean connectives. So this means the number of ands and ors and nots. And it was solved in 62 seconds. Okay, so it proved it valid. And in this case, 105 integer variables, invalid in 13 seconds. And this came from a model of the classic Hennessy and Patterson DLX 4-stage microprocessor pipeline. So here's another example. This was written by myself and also Shivendu Lahiri. And it's called Zapato, and it's used in the Windows division's Static Driver Verifier tool. And it's sort of like Euclid, but it handles also things from C. So for example, you can dereference a variable and look at its field, or you can take the address of a variable in the expressions. And this gets used a lot. So in Static Driver Verifier, when analyzing the parallel port device driver, this proof engine is called 500,000 times. Okay? And there was not one of these calls required more than 6 seconds to solve. Right? And on the average, it was a split second. We can look at the average number of variables, for example. On average, there were 25 integer variables passed through this tool, and in the largest case, there were about 1,000. Right? And on average, there were about 40 Boolean connectives, and in the worst case, there were 100,000. Right? So these are the number of ands and ors and nots in the puzzle that was presented. Okay, so now I'll talk about applications of these things. So there are lots of people around the world and at Microsoft working on these tools to solve these puzzles. And the question is, how does it affect me, as a developer of some tool, some other tool that's not necessarily interested in logic per se? So one obvious possibility is that you could perhaps use them just off the shelf, right? Perhaps in code. If you're developing code that has to solve constraints of some sort, perhaps you're doing scheduling in Outlook, or you're having to doing anything that involves finding models of constraints, then this might be a good tool for you to use off the shelf. Or perhaps you know a lot about your problem and you sort of know domain-specific things that helps you solve it in a better way. You might learn something from the implementation techniques used in these tools. And you might also use it as a second opinion during testing. Right? So I'll walk through some examples. So imagine that you are writing an optimizing compiler, and you have, for example, a set of 5 instructions in an instruction sequence. And you're trying to find a set of 3 instructions that has the same semantic meaning as these five instructions, right? So you're trying to take 5 instructions and jam them down into 3 instructions. And perhaps these 5 instructions are being used in a tight loop. So one way to solve this is to ask a proof engine, basically you try and prove that for all J1, J2, and J3, so for all possible instructions, J1 and J2 and J3, and I'm being a little bit vague here about the notation, there does not exist a J1, J2, and J3, such that the meaning of J1 followed by J2 followed by J3 on the machine, the update of that state, is equivalent to I1, I2, I3, I4, and I5, or those are those 5 instructions. Okay? So the proof engine may come back and say, yes, you're right. There is no J1, J2, and J3, in which case you can stop looking. Right? But if it says, no, that's not true, and it provides counterexamples, then you've found a J1, a J2, and a J3 that implements I1 to I5. And so now you can use that. Okay, and this technique is being used, for example, there's a project called Denali at Compaq, HP, and there's a pointer to a tech report about it. And I've also seen this technique used at Intel on IA64 instructions. So these are VLIW-like instruction sets where it's hard for the programmer necessarily to get the best instruction set encoding of the particular problem he's trying to solve. So there's some tools that people have worked on within the company for proving these optimizations correct. Another example, imagine that you are a manufacturer of a product and you're trying to ship it to various locations like Brazil and China, right? And imagine that your users give you some constraints. So they sort of like are on a website and they say, I want your tool to do this, and then I sit in Brazil, so please ship it to me. So for various regulatory reasons and standards and the particular place where the user is sitting, you might need to specialize from the available pieces of hardware and ship them the right thing at the lowest cost. Right? So this is, for example, happening at Ericsson Radio. They sell these base stations for mobile phone networks, and the companies, the telecommunications companies, will make a purchase. They're from China or from Brazil, and then they have various constraints about what they want, with the sort of characteristics of the base station that they want it to meet, and also they must meet the regulatory and standards of the particular region that they're in. So Ericsson Radio uses a proof engine for propositional logic, which is the one that was used in that competition, to automatically construct the best configuration. So the number of chords and the number of racks in the machine and the software that needs to be included. All the search space is explored, and the cheapest machine is automatically configured and mailed. So obviously, these proof engines are good for tools that are trying to do some sort of verification about software. That's a pretty natural fit. And I've told you a little bit about Static Driver Verifier, which uses this. Another example is a test that's actually here at TechFest. If you go to booth 324, there's something called Chess, which uses a proof engine that's a follow-on to the proof engine used in Static Driver Verifier. It's called ZAP. And also in test case generation, you might want to, in test case generation, want to know how can I get to E? Give me a and a B and a C such that all of this code evaluates in such a way that I can get into this conditional. Right? And so that's a proof engine can be used for this purpose also, and there's a tool called MUT at booth 322 that does essentially this. So you could visit 324 and 322 and talk to those guys about how they use the proof engines. I think in both cases they're using a proof engine called ZAP to solve this problem. So some other examples are pointer analysis. So this is where you walk over a program and you're trying to build a graph of all the possible pointer aliasing relationships in the program. That can be done. There's some work that's being done to do that with proof engines. You might imagine doing better static array bounds checking. So you might want to statically eliminate checks from your program to make sure that pointers, array indices aren't going over array boundaries. There's a company called iLog that sells tools for business rules, right? And they use proof engines essentially to solve these systems of constraints on business rules. And this allows people to describe things that the company should not or should do, right? And then these business rules are executed in this constraint engine, and then it limits the activities of people out in the field, for example. And you can imagine that if you were trying to write a game that found a good strategy, right? So you could encode that as a set of constraints and pass it to the proof engine. And if the proof engine provided counterexamples, it would give you a good strategy to use. Okay, so now I'll tell you about proof engines that are available from MSR. So, Shivindu and I and Tom Ball worked on a proof engine called Zapato, and this is the one that was used in Static Driver Verifier. And as a follow-on to that project, there's something called ZAP, which Madan Masafathi is the main developer and researcher on that project. So this, if you're interested in proof engines that support integers or reals, if you're interested in proof engines where you can put for all nested inside of your expressions, for example, then ZAP is probably the right place to look at. Okay. Now, there's a proof engine called SameST from Lintao Zhang, and he's down in Silicon Valley. So this is a proof engine for propositional logic, right? So this is the ands, ors, nots, and variables over true and false. And this is actually used quite a bit. So, in fact, ZAP and Zapato all use SameST, in fact. So this is quite a good solver. There's something called Dissolver from Cambridge. So this supports ands and ors, and it supports arithmetic. And it's the main thing about it is it supports search across multiple machines. So if you have a very, very, very large problem and you want to distribute that search, then Dissolver is perhaps the right way to go. Right? And you can work with Yusuf Hamadi on that tool. And then I'm working on something currently called Cogent, which is a proof engine specifically for expressions that show up in programming languages. So I want to specifically support pointer arithmetic, records, unions, casts, and all that sort of thing. So if you want a lot of accuracy about bit fields and integers, right? If you want to know if all of these things are true, can the third bit in this integer be true? And you want to ask that sort of question to a proof engine, then this might be the right sort of tool to use. Okay, so proof engines are software tools. They automatically solve puzzles presented in logic, right? And so you can have plus, minus, perhaps, variables over integers, perhaps variables over propositional true and false. You can have 32-bit or 64-bit signed integers, these sorts of things. And there are various. There's a spectrum of proof engines that solve different logics that you can build up from these different Lego bricks that I showed you. So we're seeing now that these proof engines are scaling to large problems, right? So for propositional logic, 10, maybe 20,000 variables. So if you can encode the particular problem that you're trying to solve as something with ands and ors and nots and variables that are bounded by maybe 20,000 variables, then this might be a good way for you to solve your problem. And within Microsoft, proof engines have really proven themselves, in a different sense of proven, in the area of program verification. So lots of people now within MSR are now using them to try and prove the correctness of programs or to try and find bugs in programs. But we haven't really explored the use of proof engines outside of program verification. So they've sort of snuck in through program verification. So I will be in Speaker's Corner here in a few moments. I'm also in an unrelated booth. So I'm in a booth about F#, which is not a proof engine. It's actually a programming language that's really good for designing proof engines. And you can also email me if you have questions. And I suggest that you go look at MUT and look at chess in booth 322 and 324. Okay? And I've tried to leave enough time for questions. Right? So I think that we'll have more than 5 minutes for questions. Okay.
Let me get a microphone to you guys.
How do you verify your proof engine?
So some proof engines produce the proof, right? So the idea of the proof engine is that it very, very, very quickly constructs a proof and then throws it away, right? And it tells you what the answer was, but it doesn't necessarily give you the proof. But you can actually grab that proof and hand that to an independent party to check the proof. So there's actually a lot of work on producing these proofs and then checking them in a smart way. Yep.
Thank you. Do you use in proof engines some sort of like branch and bound kind of algorithms, things of that sort, so that you just like lop off entire vast sections of the space?
Yeah.
Okay.
So there have been a lot of things that have happened in proof engines that have made them more powerful. But one of the most important things that people use nowadays is, imagine that you are searching this way and then you're going to search this way, and you learn something over here. So you say, what if A and B and not C are the facts that we know? A and B and not C are not possible. It's not possible for them for A and B and not C to be true at the same time. And you add that as a fact in a very smart way that sort of aligns well on the cache in the microprocessor, and store that in a smart data structure, and then remember that. And then later on, when you're exploring somewhere else, you're back to the, what if A and B and not C are true again, then you quickly eliminate that branch. And now you don't have to explore from there. Right? So if you can prune the search space like that, then it's tremendously improved the amount of search space you actually have to explore. Yeah.
And since I don't see any hands raised, another question. In terms of like optimizing for a certain objective function, like you want to maximize or minimize something like that, do proof engines use kind of like fuzzy objectives? Because like in some industrial problems, we can imagine that, like for example, in the case of rules, as they might say, instead of saying absolutely don't do this, you'd say it's desirable with some degree of desirability to avoid this or to achieve this. And so do you have these kind of fuzzy objective functions?
So in the proof engines that I've worked on, I don't try and minimize or maximize. So that's where, for example, dissolver comes in.
Yeah.
So I don't know the fine details, but I think that they're pretty. One of the ways that they get better performance is by actually not doing that sort of thing, right? So that you can say, I want to minimize or I want to maximize, but it's the language for expressing this, how you want the search space to be explored, is not very rich explicitly, because they want to make those decisions, the proof engine themselves.
Okay.
Right?